Hello everybody. In this video we'll be covering one of the sections in chapter 4 of our textbook entitled Atoms and Elements. We'll begin with a little review of what we've learned so far about atoms. Atoms are incredibly small, yet they compose everything. Atoms are pieces of elements. We'll remember that atoms go with elements, and molecules, which are groupings of atoms bound together chemically, go with compounds. The properties of atoms determine the properties of the elements that they make up. There are about 91 elements found in nature, and over 20 that have been made in laboratories. Each has its own unique kind of atom. Each of these atoms have a different structure than the others. That's what makes them different and unique kinds of elements. So there was initially a thought that matter was infinitely divisible, that you could just continue to break it down smaller and smaller. But ultimately they found that there was a particle at which point if you divided it, it would no longer have the same properties as the original material. And we have this quote down here from a really long time ago that says, "Nothing exists except atoms and empty space. Everything else is opinion." So the first person to really come up with something resembling our modern atomic theory was an English school teacher by the name of Dalton. He said that each element is composed of tiny indestructible particles called atoms. He said that they were tiny, hard, indivisible spheres. He said that all atoms of one element are identical, and he went on to describe how they are identical. So they're all going to have the same mass, volume, and other physical and chemical properties. He said that the different atoms for the different elements are going to be different from each other. So every carbon atom, for instance, is identical to every other carbon atom. They have the same chemical and physical properties. However, carbon atoms are different from the sulfur atoms. They have different chemical and physical properties. He went on to describe that atoms combine in simple whole number ratios to form molecules of compounds. And this is because he said that atoms are unbreakable, so they must combine as whole atoms. Basically, we cannot have a molecule that contains some fraction of an atom. It's got to contain one atom or two atoms or three atoms, so on and so forth. The nature of atoms determines the ratios in which it combines. Okay, so it depends on how many of each atom we have in the molecule. And the molecules that can be formed depend on the atoms that we have in it. Each molecule of a compound contains the exact same types and numbers of atoms. Okay, and this is going to lead to something we're going to talk a little bit more about later called the law of constant composition. And this led us to be able to eventually write chemical formulas for molecules. Now, in our modern world, we've actually gotten to a point of technology where we can actually visualize individual atoms. And this is actually a picture that was taken, I believe, using an X-ray photoelectron spectrometer, where IBM was actually able to place individual atoms on this sheet using lasers to move it around to spell out IBM. So now we're at a point where we can actually visualize individual atoms. Let's talk about the size of atoms. So using compositions of compounds and assumed formulas, Dalton was able to determine the relative masses of atoms. Okay, so he was actually able to figure out what size the different atoms were. He based his scale on hydrogen, which he gave a value of 1. In our modern day, we actually now use carbon as our standard, specifically carbon 12. We'll talk about what that means, but it's a specific isotope of carbon, and we say that that's exactly 12 AMU. Nowadays, we've actually able to determine the mass of atoms out to more significant digits. The unit of AMU is what we call the atomic mass unit. There's also another unit similar to the AMU called the Dalton. It's named after him, but it's actually a larger unit used often in like biochemistry and stuff. He was also able to nail down something about the absolute mass and size of an atom, and he found that they were very, very small. So the mass of a hydrogen atom is 1.67 times 10 to the negative 24, so very small grams. And the volume of the hydrogen atom is 2.1 times 10 to the negative 25 cubic centimeters. Remember, cubic centimeters is the same as a milliliter, so they are very, very small. So before we get into talking a little bit more about atoms, I want to go over a little bit of review about charges. Okay, so there are two kinds of charges. These are fundamental things about the universe. We can have a positive charge and we can have a negative charge. And they follow some pretty generic rules here. So our opposite charges attract. So positive charges attract to negative charges. We see that here. A positive charge is going to go towards that negative charge. They're going to attract each other. When we have similar charges, the like charges, they're going to repel each other. So if we have positive and positive or negative and negative, they're going to push each other away. And to be neutral, something must have no charge or equal amounts of opposite charge. So if I have a +1 charge here, a positive charge, and a -1 charge here, when they combine together, we're going to get 0 net charge for that thing. So originally there was some work done by a guy named J.J. Thomson, and he was able to prove that an atom had pieces called electrons. Thomson found that electrons are much smaller than atoms and that they carry a negative charge. Okay, and he was able to determine that the mass of an electron is 1/1836 the mass of a hydrogen atom. So it's a small fraction of the mass of a hydrogen atom. Our hydrogen atom is the lightest of all of our elements, so this is really, really small. Doesn't weigh much at all. The charge of an electron is the fundamental unit of charge that we call -1 charge. So an electron's charge is the standard for what we would call a -1 charge unit. So Thomson started to try and develop a model for what exactly an atom looked for. And he started to first adjust the first statement that Dalton made. He said that the atom is actually breakable. The atom structure has electrons suspended in a positively charged electric field. Now, he thought this, even though we'll find out that this is actually not true, because he hadn't yet discovered a particle that was positively charged. But he knew that the overall atom was neutral, so he thought there just had to be like some positive energy that was holding these electrons in place. So Thomson starts to build up a model of what he thinks a atom actually looks like, and he comes up with this very funny named plum pudding model. Basically, he thought that the mass of an atom is due to the mass of electrons, so we're going to need a whole lot of electrons, right? You're going to need thousands of electrons just to make up a single hydrogen atom. But he still theorized that there must be a lot of empty space in the atom. And he said that this must be true because the electrons are negative. We must keep them pretty far apart so that they don't repel each other and break up the atom. this is kind of a graphical representation of the plum pudding model. He just thought there was like a positively charged bubble, and inside of it is like thousands and thousands of these little electrons that are all kept relatively far away from each other. Then came a guy by the name of Rutherford. And he started saying to himself, well, if Thomson is correct and there's just a bunch of empty space, he said, how can you prove that this thing is empty? And he said, well, what if I put something through it? What if I shoot something through the atoms? Okay. So first thing he said is, well, I need the thing that I'm going to shoot to be much smaller than the atom. It needs to be able to pierce through it. So I need to use big atoms. This would be helpful, okay? And I need to use a small projectile, okay? And I'm going to have to do this with a lot of energy so that I can be sure that it had enough energy to make it through whatever positive field there is there. But I need to make sure that this thing that I'm going to shoot through it isn't so small that it's going to have like some gravitational or effects with the electrons. It needs to be able to pierce through the atom, so it needs to be small enough to get through the atom, a little bit bigger than an electron, and I got to shoot it really fast. Luckily, he actually knew how to do this. So he knew that there was this material that would release what we call an alpha particle. And an alpha particle is actually the nucleus of a helium atom. Even though he didn't really know what a nucleus or anything was, he knew that they were bigger than electrons, though still relatively small, definitely smaller than most atoms. And this is actually a type of radiation. And he also knew that it was positively charged, so he thought that would be an effective thing to use. Also, the fact that it has a charge is what helped him to project it. He's actually using a positive electric field to shoot it out. And he decides to use gold because he knows that gold is really, really heavy. So this should be a very big atom. And also, it's very, very malleable, so he could press it down into a very thin gold sheet. So this is a little difficult to picture, so we got a little image right here. So what he's got is he's got his little radioactive sample right here. That's going to shoot out alpha particles. Okay, he's got this in a lead box. He knows he's going to shoot out high energy alpha particles. He can put a little positive electric field back here. It's going to help to project it out like a little beam, okay? And then in the center here, he puts this gold foil, and then around it, he puts what we're going to call a fluorescent screen. And this fluorescent screen is going to light up when he hits it with alpha particles. So he'd been doing these experiments. He knew that he was going to be able to visualize where these alpha particles landed. So he starts hitting the gold foil. And he notices that the majority of it goes straight through the gold foil as if it wasn't even there. And it hits the fluorescent screen. Some of it, though, kind of deflects off. And it comes out at this obtuse angle here. And hits the fluorescent screen. And even smaller amount bounces back from the gold foil. And just like a ball hitting a wall and bouncing back, it comes back and hits the fluorescent screen back here. So based on these results, he drew some conclusions. He starts to say, okay, let's look at my results here. So 98% of the alpha particles went straight through. About 2% went through, but they got deflected. So that would be the ones that were deflected at the obtuse angles. And an even smaller portion, about 0.01% of the alpha particles bounced off the foil. Okay, and he's got this quote here. It says, if you fired a 15-inch cannon shell at a piece of tissue paper and it came back and hit you. So he sees that some of this is getting reflected back. And he starts to develop a new theory around this. Rutherford decides that atoms are mostly empty space, much like our plum pudding model. He decides that most of it is empty space, and he decides that must be true because most of the particles went straight through. So most of the particles were unobstructed and just went straight through the gold foil. But he also starts to decide, well, there's something going on inside of there. So the atoms must contain a dense particle that was small in volume compared to the atom, but large in mass. And this is because some of the particles bounce back. So they must have hit something in order to be able to bounce back. And he also decided that this particle was positively charged. And this is because of the large deflection of some of the particles. So he knew that there was probably some repulsive force that was causing it to deflect some of the alpha particles. So this is a little difficult again to picture. So let's take a look at a picture of what we think would have happened. So here's our plum pudding model. Now let's imagine we shoot an alpha particle through it. The alpha particle is going to go straight through, okay, because it's moving really, really fast, and it's not going to be attracted enough to any one of these electrons to hinder it. Now let's look at the idea of the nuclear atom. Well, some of our alpha particles are going to shoot straight through, right? They're not going to hit anything because there's mostly empty space here. Every once in a while, an alpha particle is going to get close to the nucleus. Because this is positively charged and the alpha particle is positively charged, it's going to deflect it away at some angle. And in a very rare occasion, an alpha particle is going to hit directly at the nucleus, and that's going to cause it to bounce back. Because this is a small amount of the overall volume of the atom, this is going to be a rare occurrence. And he starts to develop this kind of idea for what he calls the nuclear atom. So to kind of sum up what he comes up as a conclusion, he says that the atom contains tiny dense center called the nucleus. The amount of space taken up by the nucleus is only about 1/10 trillionth of the volume of the atom. So it's a small amount of the overall atom, but it is there. The nucleus has essentially the entire mass of the atom. So the majority of the mass is actually in the nucleus. We don't have these thousands and thousands of electrons to make up that mass. And he said that the electrons weigh so little, they practically contribute no mass to the atom. So he starts saying, we don't have a bunch of electrons. We have a nucleus with the majority of the mass, and then we have a few electrons hanging around. And he says that the nucleus is positively charged. The amount of positive charge balances the negative charge of the electrons. So that starts to make sense why we see that atoms themselves do not have charge. It must be that we have some kind of counterbalancing positive charge in the nucleus. And then he says the electrons are dispersed in the empty space of the atom surrounding the nucleus. Okay, and he likens it to water droplets in a cloud. So he thinks that the electrons are just kind of hanging around that nucleus on the outside. We actually know it's now a little bit more complicated than that. They're kind of orbiting in these very elaborate patterns. But he just kind of still is holding to a little bit of this plum pudding model, that we have a center with the nucleus and then some electrons just kind of hanging around. So he starts to say, Rutherford proposes that the nucleus had a particle that made up that nucleus. All right. And that it had the same amount of charge as an electron, but an opposite sign. Okay. Based on measurements of the nuclear charge of elements. So he's starting to say, okay, we have to have some kind of particle that the nucleus is made out of, and I think that particle has a positive sign. So he names these particles protons, and he says that they have a charge of +1 charge unit and a mass of 1 AMU. Okay, and remember, an AMU is based on Dalton's thing, so he's saying each one of these protons is like one mass unit of like hydrogen. So hydrogen would have 1 proton in it. Since protons and electrons have the same amount of charge, for the atom to be neutral, there must be an equal number of protons and electrons, right? So we have to have this cancellation in order to get that neutral atom. But there were some problems with Rutherford's ideas. He starts to look at them and he starts to ask himself questions like, how could beryllium have 4 protons stuck together in the nucleus? Shouldn't they repel each other, right? So if a nucleus is densely packed and it's got these 4 protons stuck in there and they're going to want to repel each other, how exactly is that working? And if beryllium has 4 protons, then it should have a weigh 4 AMU, but it doesn't. We know that it weighs 9 AMU. So where is this extra mass coming from? All right. If each proton weighs 1 AMU, and that the electrons really aren't going to be able to make up that difference in that mass, there's got to be some other kind of particle in this nucleus that also weighs something. So to answer these questions, Rutherford proposed that there was yet another particle in the nucleus, and he called it a neutron. This neutron doesn't have a charge, but it does have mass. It has a mass of 1 AMU. Okay? The masses of a proton and neutron are both approximately 1 AMU. And this really kind of helped answer both of those questions. So the extra mass is coming from the neutron, and these neutrons are packed in with the protons, and they're kind of holding them a little bit apart so that they're not so close together that they want to like blow apart the nucleus. So let's talk now about what we know to be our modern atomic theory. We know that atoms are composed of 3 main pieces. There are protons, neutrons, and electrons. We know that the protons and the neutrons are held together in the nucleus. We know that the nucleus is only about 10 to the negative 13 centimeters in diameter, so they're really, really small. And that we know that electrons move outside the nucleus with an average distance of about 10 to the negative 8 centimeters out here. So what that means is that the radius of the atom, the outside where the outer electrons would be moving about, is about 10 to the 5 times larger than the radius of the nucleus. So they're quite a bit larger. They're 10 or 5 orders of magnitude larger than the nucleus. So indeed, it is mostly empty space with this tightly packed nucleus at the center. So it is not a coincidence that electrons and electricity have a similar name. They actually are related. And electricity is actually due to the flow of electrons. And electricity actually follows some of the same rules as the charges of protons and electrons. So we still have positive and negatively charged objects. You can see this like on the 2 terminals of a battery. It is still true that charged objects repel each other, and that they can also attract each other. And when a proton and electron are paired, the result is a neutral charge because they have equal amounts of charge. Okay, so all of the things that are true of atomic particles can be scaled up to objects when we're talking about electricity in our macroscopic world. This is actually what causes lightning. So we sometimes have a negative charge buildup. We have electrons that build up inside of clouds here, particularly at the bottom of clouds. there's actually an effect where it will cause the electrons on the ground to start to move away from the bottom of the cloud. It's called capacitance, and it leads a net positive charge on the ground, and that builds up, and that builds up, and that builds up, until eventually there's so much buildup on either side that electricity is able to bridge through the air, which is an electrical insulator. That's why it builds up so much and creates this lightning that comes down and strikes the earth. There's also an electronics component called a capacitor that kind of works off of this same sort of principle. So let's review what we've learned so far about subatomic particles. We have protons, electrons, and neutrons. We have their masses here. We know that the mass of the proton and neutron is the same, and the electron is quite a bit lighter. And we can express that in both the units of AMU, where a proton and neutron are both close to 1. A neutron's a little heavier than a proton. We've actually figured that out now. And then let's talk about their location. So we know that the nucleus contains protons and neutrons, and that the electrons sit in the empty space around them. We know protons have a +1 charge, an electron has a -1 charge, and a neutron has 0 charge. And then we have these symbols that you guys should get used to where we talk about these. So a proton may be described as a P plus. Often you'll see this H plus, and that'll make a little bit more sense when we're talking about ions. But basically, because hydrogen's nucleus only contains one single proton, you could also imagine a single proton as being a hydrogen that's missing an electron. Electrons, you'll usually see these as E, or even more common with this E minus here. And then neutrons will be N or N0, where we indicate that there's no charge on that neutron. So let's do a little practice here. If it is a neutral atom, it will have, determine if each of the following statements is true about an atom that has 20 protons. Okay, so if it is a neutral atom, it will have 20 electrons. Is this true or false? That must be true, right? Because to counterbalance those 20 positive charges, we need to have 20 negative charges from the electrons. If it also has 20 neutrons, its mass will be approximately 40 AMU. True or false? That's also true, right? So protons have a mass of about 1 AMU. A neutron has a mass of about 1 AMU. 20 plus 20 is 40. And electrons are so small that they're really not going to contribute anything significant to that mass. If it has 18 electrons, it will have a net -2 charge. True or false? That's going to be false, right? If we've taken away 20 electrons, got us to neutral. If we take away 2 electrons, then we've actually made the overall atom more positive, right? So it will have a 2 plus charge, all right? So 20 plus charges, less 18 negative charges leaves us with a net 2 plus charge.